Hi everyone. In this video I'm going to demonstrate how to use SPSS in order to carry out principal components analysis. Before we get started, let me note a few things. First, a copy of the data and this PowerPoint will be provided underneath the video description. Although I'm not going to spend a lot of time on the PowerPoint in this video presentation, this PowerPoint will contain a lot of information that you may find useful. In particular, there is a lot of information regarding how to interpret various pieces of output, and there's also extensive citations throughout. So certainly consider downloading the dataset and this PowerPoint to further your learning. Additionally, let me note that the example that I'm using and the data is actually coming from a presentation at this website right here, and I'll include this link underneath the video description. But this is from the UCLA Institute for Digital Research and Education, where they are talking about principal components analysis, and they provide annotated output. My PowerPoint actually goes into a lot more detail, but this is also a useful place to look in terms of furthering your learning. So certainly check it out. They have not just they not only have useful information on this particular topic, but a lot of different topics related to statistics. So here's a copy of the data that I downloaded from that website, and we have items 13 through 24 are basically appear to be measures of student perceptions of their instructor and of their course. And I'll just kind of show you really quickly. For item 13, you can see that it says instructor is well prepared, instructor has scholarly grasp, instructor confidence, instructor focuses lectures, and so forth. So what we're going to do is carry out a PCA involving items 13 through 24. So what I'm going to do is I'm just going to click back over here, and we're going to go to Analyze. We'll go down to Dimension Reduction and then Factor. So we'll click on that button, and I'm just going to scroll down a little bit and find the item. So we have item 13 right here, and I'm just going to highlight all of these items all the way up to item 24, which is this one right here. So I'm going to move those variables over. Under Descriptives, there are a number of different descriptive statistics that we can ask for. We could ask for univariate descriptives, which would give us means, standard deviations, and sample sizes for our variables. I'm going to actually leave that unclicked. They present it on that particular website, but it's a lot of information that I really just don't want to have in this particular output. Additionally, we could ask for correlation matrix and significance tests if we want those. Again, I'm not going to click on those just to kind of keep the output a little bit more compact. I am going to click on KMO and Bartlett's test of sphericity and the anti-image matrix. So I'm going to click on Continue. Under Extraction, you'll see that the default extraction approach is actually principal components. And what I'm going to do is go ahead and click on Scree Plot. Now you'll notice under here as well, underneath Extract, we have based on eigenvalue, eigenvalues greater than 1. And this is the classic eigenvalue cutoff rule, which basically is used to retain those components that have eigenvalues that are greater than 1. So this is one way that we might make a determination as to how many components to retain. If we want to force a component solution, then we could click down here where it says fixed number of factors. Basically, in this case, it would be components, and we could actually force a certain number of components. So, for instance, if I wanted to force a 2-component solution, I could click down here and then type in 2, and that would give us our 2-component solution. I'm not going to do that for this demonstration right now. We're just going to stick with the eigenvalue cutoff rule right here. We'll click on Continue, and then actually, as you're going through and thinking about the process involved in carrying out components analysis, it's really easy to go through a number of these buttons and just kind of click a number of defaults. And really the first decision that you have to make, or one of the first decisions that you have to make, concerns how many components to retain. And once you've sort of done that, then you make decisions concerning how to interpret or name those components. So I'm actually just going to start off with just the basics again, using the eigenvalue cutoff rule. The other approach that we could use is the scree plot in order to help determine the number of components to retain. And then once I've made those determinations, then I'll bother with going through the rotation button. So I'm going to click on OK. And now we get our output. So the first thing I want to draw your attention to in our output is the KMO and Bartlett's test. And so basically, KMO is Kaiser Meyer-Olkin measures of sampling adequacy. And Bartlett's test is basically a test of the correlation matrix, or sample correlation matrix against an identity matrix. So basically, these are useful for determining whether or not it was even appropriate to carry out a components analysis on our data. And so, again, there's more detail in the PowerPoint on these measures, but basically what we're looking for right here, at a minimum for the KMO, we're looking at for a minimum of 0.50, and that is actually still considered pretty poor in terms of, you know, the appropriateness of carrying out the analysis, but is still, you know, would be deemed acceptable using some conventional standards. Generally speaking, though, these values would range between 0 and 1, and so the closer to 1, the better. With Bartlett's test, this is a significance test of our correlation matrix in relation to an identity matrix. So if this is statistically significant, then that's actually a further indication that it was actually appropriate to carry out the components analysis on our correlation matrix. Additionally, we can look at the anti-image matrix, and in particular look at the principal diagonal within this within our anti-image correlation matrix. So I'm going to scroll down here, and what we're looking for are values that are closer to 1 as well. So we're basically using the same kind of criteria that we would use with the Kaiser Meyer-Olkin measure that we just talked about. So this is basically that measure, but applied to the individual items in our data. And so what we're going to do is you can see right here all of these values are very close to 1, which is signifying that we have good measures that are included in our component analysis. So now I'm going to scroll down, and we'll look at, first off, at the this information right here. So where it says total variance explained, you'll notice that we have 12 components that are listed, along with their respective eigenvalues. So the deal is that the number of components that you have in the model is going to equal the number of measured variables that's included in the analysis. The eigenvalues are basically summarizing the variation in the items that are accounted for by the components. So essentially what we're doing is we're repackaging the variation in the original set of measured variables into components. And the idea is that we're trying to select the number of components that does the best job of summarizing the overall variation in those measured variables. So if we look at the eigenvalue right here, we could see that component 1 would account for about as much variation as 6.2 of the original measured variables. Component 2 accounts for a little bit over, basically as much variation as a little bit over 1 of the original measured variables. And you see with component 3, we're actually accounting for less variation than a single measured variable. And so the eigenvalue cutoff rule that I was telling you about is being applied over here where it says extraction sum of squared loadings, and you'll notice that we have 2 eigenvalues that are given. Essentially, these are the same eigenvalues that you see over here in this portion of the table, and that's because both of these eigenvalues are greater than 1. And essentially the eigenvalue cutoff rule, or the Kaiser criterion, essentially states that a component, for it to be retained, should account for at least as much variation as a single measured variable. So in both of these cases, we have essentially a 2-component solution that is suggested. And you can see also, in terms of the percentage of variance in the original measured variables accounted for by the components, we have 52% based on component 1 and a little bit over 10% based on component 2. So combined, those 2 components account for roughly 62% of the variation. So at least using the eigenvalue cutoff rule, or again the Kaiser criterion, that would suggest a 2-component solution. We can also look at the scree plot that's given, and you can see that we're essentially plotting the component numbers, and the eigenvalues. So the basic idea is that when we're looking at the scree plot, it's like looking at the side of a mountain. So you can see that on the primary slope right here, you see really the primary components. So because these have the largest eigenvalues. And then where the mountain sort of begins to approach sort of a rubble at the base of the mountain right here, these are more trivial components in terms of summarizing the variation. So the basic idea is that when we're looking at the scree plot, what we're going to do is basically make a cut point where the rubble begins at the base of our mountain, so to speak, and the eigenvalues are falling on the primary slope on our mountain. So based on our scree plot, it would appear that we have evidence of a two-component solution as well. Do note that component 2 still has a fairly small eigenvalue relative to component 1, but it does look like there is still a fairly minor second component that might be useful in our analysis. Now, there is another possible approach to evaluating how many components to retain, and that would be parallel analysis. And unfortunately, SPSS does not include that particular option. There are some syntax-based approaches. You can actually download a syntax file from Brian O'Connor's web page, and you can run parallel analysis. Basically, what you're going to be doing in that case is generating random eigenvalues, and you're comparing those random eigenvalues against the eigenvalues that are extracted from your data. And the basic idea is that you retain those components where the eigenvalues from your data exceed those that are generated at random. So although we can't do this directly in SPSS, we can actually go to a website. This is a nice little site right here, and I'll include a link to this underneath the video description as well. And this is basically a parallel analysis engine, because basically what we need to do is just to generate random eigenvalues. So where it says number of variables in your data set to be factor analyzed, I'm going to type in 12. We had 12 variables right there. And then all of a sudden you see a change over here that gives us 12 components that are being reflected. Then we have to include our sample size. And our sample size for this analysis is 1428, so it's quite a large sample size. Where it says type of analysis, we're going to leave it set at principal components. Where it says number of random correlation matrices to generate, the default is 100. If we wanted to set this higher, such as 500, we could certainly do that. And as we make changes on the left, you see it reflected in the right. And then we also have percentile of eigenvalues. The default is 95th percentile. So one option is we could use the mean eigenvalue or percentile eigenvalue. And so what this is really reflecting is the idea that we randomly generate, in this case, 500 correlation matrices and compute the eigenvalues for our 12 components associated with each of those correlation matrices, and we could either use the mean of those random eigenvalues or we could use the 95th percentile. And generally speaking, it looks like nowadays the 95th percentile is more recommended. So we're going to use that in making our decision as to how many components to retain. So you can see right here that the random eigenvalue associated with the first component is less than the eigenvalue from our data for that first component. So at this point, we can retain the first component from our data. The second random eigenvalue, you can see it is actually, again, less than our eigenvalue for the second component, so we would retain two components. But you see the random eigenvalue for the third component exceeds the eigenvalue for the third component based on our original data. So what that would suggest then is that we make our cut at after the second eigenvalue. So basically we would retain two components when we are carrying out this analysis. And so what we'll now want to do is to interpret those two components in light of the fact that our scree plot, our eigenvalue cutoff rule, and even our parallel analysis, they basically all agreed. Now let me just note that it's not always going to be the case that you'll have agreement across the three, and so you'll have to sort of make a decision among those three as to maybe which approach you would favor more when it comes to deciding on the number of components to retain. So given that we're going to stick with our two-component solution, the next thing I'm going to do is I want to interpret those components. Now, it just so happens that using that eigenvalue cutoff rule, we already extracted and retained two components right here. So if we scroll down, you'll see there's a matrix that is the component matrix, and this is unrotated loading matrix. And basically, this is not particularly helpful when it comes to interpreting the components. So typically what researchers will do is they will perform some type of rotation in order to increase the interpretability of the components. So to do that, what I'm going to do is go up to Analyze, go back and rerun the analysis. I'll go back under Extraction. And if it were the case where two components were not suggested, maybe by the parallel analysis, and basically nothing agreed, then it may be the case where I would come down here and I would click on fixed number of factors or components to extract, and I would force that solution. So in this case, I will go ahead and force a two-component solution, but not really a whole lot of need to, because the eigenvalue cutoff rule already would provide that for us. But I'm going to go ahead and stick with this, and we'll click on Continue. Under Rotation, we have various options. So we have Varimax rotation, we have Promax rotation, and some others. So there are two general classes of rotations that are available. The first type is orthogonal rotation, and basically what that means is that the components that are rotated will remain uncorrelated. So when you first extract those components, so kind of going back up to our previous table right here, essentially the variation accounted for by each of the components that are extracted is additive. So we can talk about the percentage of variation accounted for by each individual component, and then if we take the percentage of variance accounted for by each of them, they would sum up to 100% of the variation in the original set of measured variables. And so if we perform an orthogonal rotation, then it maintains that additivity with respect to the variance that's accounted for. A second class, though, is oblique rotation, and that essentially allows the components that were originally orthogonal to be correlated. And so if we go back under rotation, a common type of orthogonal rotation, is the Varimax rotation, and a common type of oblique rotation is Promax. So I'm going to really start with Varimax right here. I'm going to click on Continue and on OK, and just kind of scroll down, and you can see that basically in our table now where it says total variance explained, we have again our initial eigenvalues. These are the eigenvalues for the components that are retained, and percentage of variance accounted for, cumulative percentage of variance, and so forth. Over here we have rotation sum of squared loadings, which include the eigenvalues for the rotated components, and then percentage of variance accounted for, and then the cumulative percentages. And you'll note that the cumulative percentage of variance accounted for pre-rotation and post-rotation is exactly the same. But the eigenvalues look a little bit different, and the percentage of variance looks a little bit different as well. And basically we're redistributing the variance that's accounted for by the components that have been rotated. So I'll scroll down, and now you can see that we have our rotated component matrix. And so this is essentially a structure matrix that reflects the correlations between each of our measured variables and the components themselves. And we use those loadings in order to provide a name for those components. So what we're trying to do is to describe what these components actually mean. So there are a variety of loading criteria that have been suggested in the literature. What I'm going to use is a loading criteria of 0.40 in absolute value to retain a measured variable on a given component. And so I discuss a lot of these issues in the PowerPoint. So you can see that this first variable, instructor was well prepared, meets the loading criteria on component 1 and does not meet the loading criteria on component 2. Instructor has a scholarly grasp, loads onto component 1, does not meet that criteria on component 2. Confidence meets the criteria on component 1, does not meet the criteria on component 2. Instructor has focused lectures, meets the criteria on 1, does not meet the criteria on 2. Uses relevant examples. Now in this case you can see it meets the loading criteria on both components 1 and 2, and this is basically a complex variable, and this makes it a little bit more difficult to determine how we should use this variable when it comes to naming those components. So one strategy is just to say that, well, because it meets the criteria on both components, then we don't use it at all since it's not helping us to differentiate between the components. Another option is to look at the differential in the magnitude of loadings, and if the differential is, say, less than 0.30, then we would, again, treat it as not being useful for making distinctions between the two components. And that's really what is the case here. So I'm going to actually ignore this variable when it comes to interpreting the components. This next component meets the loading criteria on component 2, but not on 1. Instructor allows me to ask questions, meets the criteria on 2, but not 1. Here we have 2, but not 1. Here we have another complex situation, and so there's not really much of a differential between the loading, so I'm going to remove this item from consideration when naming. This next one meets the criteria here, does not meet it here. Again, another complex variable, and also right here as well. So at any rate, as we're looking and naming our components in, we already know that these items right here are not going to be useful when it comes to naming the components. But you can see that really the first component reflects really more of the instructional effectiveness. And so the second component really kind of measures more of a student-centered sort of perspective with respect to, well, again, with students. So I'm going to name the first component perceived instructional effectiveness and the second component perceived student-centeredness. Now, given that naming, if I wanted to use the components in another type of analysis, such as regression analysis, I could easily do that. The way that I would do that is to when I run my analysis, go back to Analyze Dimension Reduction Factor, and I'll leave the rotation, everything the same, but I can click on Scores right here, and I can click on Save as Variable. So I can save the component scores to my data set. And I'll click on Continue and then on OK. And so now in my data set at the very end, you can see that I have two columns reflecting the component scores. So what I'll do is I'll go ahead and rename these. I'll just really demonstrate how I could use them. So I'll just call the first one Perceived Instructional Effectiveness, and the second one we'll call Perceived Student Centeredness. And I'm just going to go ahead and remove the label right here for each of those two variables. And let's say that I want to predict student GPA. There's actually student GPA is in here. And so that's what we're going to do. We're going to predict this variable right here. So what I'll do is I'm just going to go through and run the regression analysis. Click linear right here, and we'll move student GPA over to this box, and I can scroll down here and I can move my two predictor variables over to the independent variable box, run the analysis, and you can see that basically there's a pretty low R-square. They're not really doing anything, which I wouldn't necessarily expect, but this was just kind of demonstrating that we could use the components in a subsequent analysis. But nevertheless, and it may be a little hard to see, but you can see down here, perceived student centeredness is a significant, positive predictor of GPA, whereas perceptions of the instructional effectiveness was unrelated to student GPA. Now, one final thing that I want to show you is how to carry out an oblique rotation. So I'm actually just going to remove this altogether, and I'm just going to rerun the analysis using oblique rotation. So in this case, I'm going to click on rotation. And again, there are various types of oblique rotation. I'm going to stick with Promax rotation here. We'll click on continue. Under scores, I'm actually just going to click off of this and click on continue. So now when I scroll down, you'll notice that first off in this table, variance explained, you'll notice that we don't have all that information that we had at the end of the table when we had orthogonal rotation, basically our Varimax rotation. In this case, we have rotation, sum of squared loadings. These are the eigenvalues associated with the two components, but the eigenvalues are actually computed essentially by squaring and summing the structure matrix, which I'll talk about shortly. But this does not really address the intercorrelations among our rotated components. So we can't really talk about the variance accounted for by the rotated components in an additive sense. So there's a lot more ambiguity when it comes to interpreting analyses involving an oblique rotation. But I'll scroll down and you'll notice that again we have our unrotated component matrix. Then we also have our structure matrix, which is containing the correlations, the zero order correlations between each of our measured variables and the components themselves. But these correlations don't account for the fact that the components themselves are intercorrelated. So if we want to look at the unique relationships between the measured variables and each individual component, basically, looking at the relationship, say, between this variable and component 1 while controlling for the overlap or the shared variation between components 1 and 2, then the pattern matrix is the best way to go. And so if we use, and so commonly, or pretty much most commonly, when it comes to interpreting your matrices following an oblique rotation, the pattern matrix is more commonly used. And so you can see right here, using our same 0.40 threshold, that this variable instructor was well prepared, instructor had a scholarly grasp, instructor confidence, focus lectures, instructor uses clear relevant examples. All of those load pretty unambiguously onto component 1, whereas sensitivity to students, allows me to ask questions, accessible outside of class, aware of student understanding. Those are all pretty unambiguous indicators of with respect to component 2. And then you can see right here, I'm satisfied with students' performance evaluation, meets the criteria on 2 but not 1. And then also this last one, compared to other instructors, the instructor is there's not really a lot more description on that variable in the example data and so forth. But basically, again, component 1 seems to largely reflect the perception of instructional effectiveness, and component 2 seems to largely reflect the perception that I guess that the instructor is more student-centered. If we scroll down a little bit further, it's a little hard to see on here, but you have the component correlation matrix. So this is the correlation between components 1 and 2, which is 0.639. So we can interpret that to mean that perception of instructional effectiveness is pretty substantially correlated, positively so, with perception of the instructor as being student-centered. The last thing that I want to draw your attention to in the output, which I haven't really talked about at this point, are the communalities. And so communalities basically reflect the proportion of variation in each of these measured variables that's shared with the components that are retained in your solution. The initial communalities will always be 1 in the PCA, and under extraction, these communalities reflect, again, the shared variation between each of the measured variables, and in our case, our 2 retained components. So you can see that the instructor well-prepared variable shares approximately 73% variation with our 2 components, or you could say that the 2 components account for about 73% of the variation in that first variable. They account for roughly 69% of the variation in instructional. The instructor has a scholarly grasp, about 65% of the variation in instructor confidence, and so forth. So that is a really quick run through. It may seem a little bit long because there was a lot to talk about, but that was a quick run through of principal components analysis using SPSS. Again, I encourage you to download the SPSS data file and the PowerPoint in order to follow along and to get a lot more information that I could really talk about in this video. So I appreciate you watching.